Okay, so here's a Zoom meeting for Physics 232C. We're studying chapter 23 on modern physics. So we'll go over a couple of problems from chapter 23. The reading quiz is due tonight. The problem set is due Wednesday. We'll go over a couple of the problems on the problem set. Chapter 23 is called Modern Physics. It's probably a better term would be 20th century physics. Most of the topics in this chapter were discoveries in the 20th century, but earlier part of the 20th century, not the later part of the 20th century. So you might call this early modern physics. The first section explains that quantization, the fact that certain physical quantities, many physical quantities, are quantized, was sort of one of the beginnings of modern physics. What does quantized mean? It means that they don't form a continuum of values. They just have a discrete set of values. And mentions here, here's a picture from the summary, mentions here mass, elementary particle. Let's take electrons. All electrons have the same mass. There's only one mass for electrons. Protons are the same. So masses have definite value, have only particular values. You can't have masses of all possible values, at least not at the atomic scale. Another example is charge. All electrons have the same charge. Same for protons. So charge is quantized. It's only certain discrete values. Then the next section is on black body radiation. And that was really the first phenomenon where this idea of quantization was applied to energy. And the physicist who came up with the explanation of the black body spectrum was Max Planck. Max Planck, well, experimenters had measured the spectrum of radiation from a black body at temperature T. And the old theory of radiation did not agree with the measured distribution. So here's the distribution of intensity as a function of wavelength for different temperatures, objects of different temperature. Now these should be absorbent objects. Well, that's why we call it a black body, because the object absorbs light. That makes it black. But if it has a temperature T, it radiates light, or it radiates electromagnetic waves, which might not be in the visible spectrum. They might be in the radio or infrared spectrum. The distribution depends on the temperature. It has a maximum, and beyond that, it has a maximum as far as wavelength is concerned. And for wavelengths beyond that maximum wavelength, as the wavelength increases, the amount of radiation decreases. The peak of the spectrum, or the maximum of the intensity as a function of wavelength, is given by Wien's law. So here's one of the constants you'll be using, Wien's constant. .898 times 10 to the minus 3 meters times Kelvin. Kelvin's a degree Kelvin temperature. So for a given temperature, the position of the maximum of the intensity spectrum has a certain value. And as T increases, the wavelength decreases. The wavelength of the distribution decreases. So here's 1, 2, 3 different temperatures, and you see how the distribution changes. For one thing, the intensity increases with temperature. For another thing, the position of the maximum wavelength decreases with the temperature. Now, integrating over all possible wavelengths gives the total power. And the total power is given by the Stefan-Boltzmann law. And here's another constant you'll need to use. Stefan-Boltzmann constant. The constant is not given in this page, but it's that it's represented by the Greek letter sigma. Wien's constant, 2.898 times 10 to the minus 3 in the standard unit, is usually represented by B, the letter B, lowercase b. Now, Planck explained this by assuming that energy is quantized. The energy of radiation is quantized. So in other words, the energy is proportional to the frequency. For a given frequency, you can only have energies which are multiples of that frequency. And the quantum would be the frequency times a universal constant called Planck's constant. So here's another constant you're going to have to know. Planck's constant, H, which is extremely tiny in terms of everyday units, like joules and seconds, but it becomes very important, not so, it's a negligible quantity for everyday energies and times, but for atomic systems, which have very small energies and very long time and very small times, H has an importance. So atoms are described by quantization. We'll come to atomic physics in the next chapter. Now, that was the start of quantum theory. It was extended in various ways, and one way was Einstein's theory of the photoelectric effect. The photoelectric effect is that when light strikes a metal, it can liberate electrons. So light of a high enough energy, that is to say, light of a high enough frequency, striking a metal surface can liberate electrons. So if you have a cathode ray tube and you shine light on the cathode, electrons will be emitted and then they'll be repelled from the cathode. Cathode is the negatively charged electrode. They can flow to the anode, you can measure the current, and so you can measure various quantities about the process or the phenomenon of the photoelectric effect. And again, Einstein explained this based on Planck's theory that radiation energies are quantized. So the name photon became the name for the smallest excitation of light. If the light has a wavelength of lambda, it has a corresponding frequency of f. The energy is given by Planck's formula h times f, where h is that same universal constant. So Einstein explained what's happening just on the basis of conservation of energy. The radiation comes from quantized energies, those are the photons, and energy is conserved. So the kinetic energy of the electrons that are emitted by the metal will be the energy of the photon minus the binding energy. In other words, the photon has to have enough energy to liberate the electron. And that binding energy is called W0, the work function. It was for this explanation of the photoelectric effect, which really proved the photon theory that was earlier proposed by Planck. That's why Einstein got the Nobel Prize. Another proof of the reality of photons, the quantization comes from the fact that light is a stream of particles. We've described light as a wave phenomenon, but in another way, it can be looked at as a stream of particles. Those are the photons. And the really critical experiment verifying the reality of photons was Compton scattering. Compton was an American physicist. Compton showed that when a photon hits an electron, it scatters just like if it had particles, just like it was a particle hitting a particle of charge, an electron. And so he could analyze the energies, and in the photon theory, energy is related to frequency or wavelength. He could analyze those energies just using the classical theory of scattering of particles. And that the fact that the experiments agreed with his analysis pretty much proved that indeed light is a stream of photons. The final section, I guess it's the final section, the section 4, is on wave-particle duality. Well, light can in some ways be looked at as a wave, but in some ways it can be looked at as a stream of particles. So there are particles and waves, and you can't say whether light consists of a wave motion or a particle motion. In some ways it's one, and in some ways it's the other. So there's this wave-particle duality. And the French physicist Louis de Broglie, proposed that the same should be true for massive particles. Take an electron. We think of the electron as a particle. It has a certain mass. But it can also be described as a wave in some way. De Broglie didn't have a complete theory, but he proposed there's some sort of wave associated with the motion of an electron. And the wavelength is given by h, that same universal constant that Planck had introduced, divided by p, where p is the momentum. Remember from physics 231, momentum is mass times velocity. And then some years later, the development of a full quantum theory, one of those physicists was Heisenberg, and Heisenberg related the de Broglie wavelength to uncertainties of position and momentum. And the Heisenberg uncertainty principle says that the uncertainty in momentum multiplied by the uncertainty in position must be greater than or equal to h over 4 pi. H is that same universal constant, Planck's constant. So all of quantum mechanics is based on the value of h, which in everyday life, in terms of everyday measurements, is extremely small. So we really don't observe quantum effects in everyday life. But on the atomic scale, h has a scale of energies and times on the atomic scale. And so it's crucial for anything involving atoms. And we'll come to atomic physics next week. All right, so that's kind of a quick overview of chapter 23. You should have read the chapter already. The reading quiz is due tonight. Let's go on and look at some problems. So you all already know the equations because you've read chapter 3. You should have taken notes, so you've got the equations written down in your notebook. So let's just take a look at a couple of problems and see how they would be done. So here's a problem from the assignment, problem 22. An 800 milliwatt laser produces 532 nanometer green light. How many photons does it emit each second? So here's the laser beam. Well, it's drawn as if it's red. It should have been drawn as if it was green, but anyway, here's the laser beam. It's a stream of photons. Each photon has a certain energy, and Planck's law says it's the Planck's constant h times the frequency. And of course, for any kind of, now, light is also a wave. So light has a frequency, it also has a wavelength. And the relation between frequency and wavelength is always the same. Frequency times wavelength is the speed of the wave. Now, the speed of light is the universal constant c, 3 times 10 to the 8 meters per second squared. So the frequency is c over lambda. Now, we're given the power, so we write the equation for the power. Well, it's the energy in one photon times the number of photons divided by the emitted in a given time, divided by the time. So we're going to refer to 1 second, so let delta t be 1 second. We want to know the number of photons that are emitted, so let's solve this equation for delta n, the number of photons, multiply both sides of the equation by delta t, p delta t, that'll be the amount of energy, divide by the energy of one photon, that's E gamma. Now, E gamma is hc over lambda by Planck's law, h times the frequency. So that's the answer. Now you have a formula, you just have to do the calculation. So if we take the numbers given in the problem, P would be 80 milliwatts. The time would be 1 second. We divide by HC. Now HC has a simple value. HC is 1240 nanometer electron volts. So this is using electron volts as the unit of energy. And then divided by 1 over lambda. So we put lambda in the numerator, let's say 530 nanometers. Now we're going to have to convert units because the numerator is in joules. Watts is joules per second. And the denominator is in electron volts. So we should divide by the fraction. 1 electron volt is 1.602 times 10 to the minus 19 joules. So this factor is just a conversion factor. It's equal to 1 because the numerator is equal to the denominator. So we're just multiplying by 1. Well, that doesn't change the number. It changes the number, but it doesn't change the quantity. It changes the units. So now if we look at the units of watts is joules per second, so watts times seconds here would be joules. That'll cancel the joules in the denominator. Newton meters will cancel the Newton meters in the denominator. Electron volts will cancel the electron volts. So the dimensions will all cancel out. We just have a number. And you can do it with a calculator. You can just kind of estimate it. it'll be something like 2 times 10 to the 17, which is, of course, a very large number. So laser light consists of a stream of photons, and the number of photons is incredibly large. It's 2 times 10 to the power 17. Here's another problem from the problem set, which is due Wednesday. Problem 79 from the book. Suppose an electron is confined in a box. Let's say the box has a volume L by L by L. What's the uncertainty of the electron momentum? Now, of course, momentum is a vector, so there'll be one for each dimension. The uncertainty in px, the uncertainty py, the uncertainty pz. Suppose each momentum component is just equal to the uncertainty value. Then what's the electron energy? And then the third part of the question, for what wavelengths would a photon have the same energy? What's given in the problem is the size of the box. It's L by L by L, and L is 0.04 nanometers. Now, you know, the typical size of an atom is 0.1 nanometers. So this is sort of the typical size of an atom. So you're confining this electron into a volume the size of an atom. It must have kinetic energy by the Heisenberg uncertainty principle. It must have momentum. It must have kinetic energy. According to the Heisenberg uncertainty principle, delta x times delta p has to be greater than or equal to h over 4 pi. Now, delta x is just L. It's somewhere in there, but we don't know exactly where. So we'll say the uncertainty in x is L. So delta px is h over 4 pi L. And same for delta py, and same for delta pz, because it's a cube. So we're going to say px, py, and pz are both, well, it could be plus or minus. The uncertainty is h over 2 pi L. I don't know if it's moving upward or moving downward. I don't know what directions it's moving. So I could just say px is plus or minus h over 4 pi L. And now the kinetic energy is p squared over 2m. 1 over 2m times px squared plus py squared plus pz squared. You may remember from Physics 231, kinetic energy is 1/2 mv squared. And momentum is m times v. So m times v squared is p squared over m. So kinetic energy is p squared over 2m. And then there are 3 components, so you have to add them together to get the total energy. So we got 3 times 1 over 2m h over 4 pi L squared. And the plus or minus doesn't matter because I square it. Now I have to calculate this quantity. Now you could look up h in SI units, and you could look up m in SI units. Remember, h is very tiny in SI units. It's 6 times 10 to the minus 34. M is very tiny in SI units. It's 9 times 10 to the minus 31 kilograms. L is very tiny because L is only 0.04 nanometers. It's the size of an atom. So you could do this calculation with your calculator using SI units, but there's an easier way. Multiply the numerator by c squared and multiply the denominator by c squared. This becomes 3/2 mc squared, the denominator, hc over 4 pi L squared in the numerator. Now remember, hc has a simple number, a simple value, 1240 in electron volt energy units. So hc is 1,000 is 1,240. If I use electron volts for the energy and nanometers for the distance, now I know the distance. That's given in nanometers. So this HC over 4 pi L, the nanometers will cancel. And what I'll have will just be electron volts squared. Now, what about MC squared? Well, from relativity, E equals MC squared. And for an electron, MC squared is about 0.5 times 10 to the 6 electron volts. So this number has a simple value, 0.5. And unit MC squared, unit electron volts, so times electron volts squared will give me the answer in electron volts. So question B is, what is the electron energy? Well, it'll be that energy. It'll be some simple number if I use the electron volt. Now it says here, does your answer make sense? Well, since this is all atomic scale, you should get an energy, which is sort of the order of atomic scale. And the atomic scale for energies is electron volts. The energy levels in an atom are separated by electron volts. We'll come back to atomic physics next week. Here's a problem on the photoelectric effect. So this is problem 90 in chapter 23. It's assigned on the problem set. A photocathode emits electrons with maximum kinetic energy K max when illuminated with ultraviolet light of wavelength lambda. K max is given, 0.5 electron volts. Lambda is given, 300 nanometers. That's below the visible spectrum, so that's an ultraviolet wavelength of light. Now the question is, what's the threshold wavelength for this metal? So that's what we're trying to calculate. We're trying to calculate lambda threshold. What does this mean, threshold? Well, you'll read about that in the section on photoelectric effect. Electrons will be emitted if the wavelength is short enough. If the X-ray wavelength, if the light wavelength, probably an ultraviolet wavelength, is short enough. That was what we're trying to calculate. What's that maximum possible wavelength that will emit electrons? Now we're told that a wavelength of 300 nanometers does emit electrons, but it emits electrons where the electron kinetic energy can be as high as 0.5 electron volts. So we're going to have to analyze this in terms of several parts. I mean, we always start by drawing a picture. So here's a picture. We have ultraviolet light shining on a metal surface, and electrons are being liberated. Now, Einstein's theory of the photoelectric effect says that the maximum kinetic energy is the photon energy minus the binding energy. In other words, if the photon has enough energy to overcome the binding of the electron in the metal, it will liberate the electron with some kinetic energy. Now, the electron may lose some of its kinetic energy as it exits from the metal surface. I mean, the electron is bouncing around inside the metal. It's in an atom, actually. it's in one of the metal atoms, the light will be absorbed by the electron. It will be liberated from the atom. It'll bounce around inside the metal, and eventually it'll come off the surface. Now, it may lose some energy as it bounces off along the by the electrons inside the metal. The maximum energy that it could come off with would just be the energy of the photon minus the binding energy. That would be if the light hit a metal right near the surface, so it just has enough energy to be liberated from the surface. That's called W0, the work function. It's the amount of work to liberate the electron, so it's the work function. And it didn't lose any energy bouncing around inside the metal, so that would be the maximum kinetic energy it could come off with. That was Einstein's theory of the photoelectric effect. All right, so that's one equation we know. Now, we're not given the frequency, but we are given the wavelength, so we can write the frequency as c divided by the wavelength. We know K max. We know lambda. That's not what we're trying to calculate. What we're trying to calculate is a different lambda, the threshold lambda. Just enough energy to release an electron, but not with this maximum kinetic energy. It could just have zero kinetic energy. So here's the calculation. What we're trying to calculate is the threshold wavelength. That's the maximum value of the wavelength that will produce some electrons. Not with this kinetic energy, but with a lower kinetic energy. This is the maximum kinetic energy. So this is the maximum value of wavelength for which photoelectrons can be emitted. So first of all, the kinetic energy of the electron has to be greater than zero because kinetic energy is a half mv squared. That's always positive. It has to be less than K max, which is HF minus W0. That's Einstein's equation. Now we can use the second part of this expression to determine W0. We're not told what W0 is. That depends on what the metal is. Well, we're not told what the metal is. So we don't know the work function. That's one of the things we'll have to calculate. But we can do that from Einstein's equation. Just by algebra, W0 will be H, F is C over lambda, minus K max. So that calculation, so that equation tells me W0. Now, second step, I want to know lambda threshold. Lambda threshold is when the electrons come off with zero kinetic energy. You know, kinetic energy must be greater than zero. So HF has to be greater than W0. Just think about this equation where we put W0 on the other side of the equation. On the other side of the equation, H has to be greater, put the W0 over here, HF has to be greater than W0. It has to have enough energy to overcome the binding energy, but not giving the electron any extra kinetic energy. So F has to be greater than W0 over H. Lambda is C over F. So that means lambda has to be less than C over W0 over H. This inequality means if I put it here, C over lambda, move the lambda to the other side of the equation, of the inequality, move W0 to the other side of the inequality, we find lambda has to be less than HC over W0. So this would be the threshold. The X-ray has to have a short enough wavelength so that it has a high enough energy, because energy goes like frequency, frequency goes like 1 over wavelength. So this is what we're trying to calculate. So let's try putting in the numbers. W0 is HC over lambda. Now HC is 1240 if I use electron volts for the energy scale. So that's 1240 electron volts, nanometers, divided by lambda was 300 nanometers. So the nanometers cancel, I get electron volts. And I have to subtract off W0. No, I have to subtract off Kmax. Kmax is 0.5 electron volts. So using electron volt scale, W0 will be 1240 divided by 300 minus 0.5. That's 3.6 electron volts. And now what about lambda? Well, lambda, the threshold lambda has to be HC. Now again, HC has a simple value, 1240, if I use electron volts. And now W0, I just calculated in electron volts, so I can put in 3.6 electron volts. Now the electron volts will cancel numerator and denominator, and then from the numerator, I'll get nanometers. So that'll come out to be, say, in this case, 344 nanometers. You notice that this wavelength is indeed less than the threshold. All right, so that's modern physics, or at least 3 examples of modern physics. And you have to read through chapter 23 and do the problems from chapter 23. Next will be chapter 24, which is atomic physics. And the problem set for modern physics and atomic physics are combined. So you're in problem set number, whatever it is, there'll be a set of modern physics questions plus a set of atomic physics questions. And we're coming up to exam 3. So, you know, you're going to have to read also chapter 24 to prepare for exam 3. We'll go over that next week. So we'll go over problems like this, which are again the same problem set, but for the chapter 24 part. We'll go over those next week.